Hello, everyone, and welcome to this presentation. As part of the 4D Summit 2020, I'll be presenting under the title of 4D for IoT, an Internet of Things solution. I'll start by briefly presenting myself. My name is Mahdi Bakkali, and I'm a technical support engineer in 4D. And I work mainly with our customers based in Latin America and Spain. I'll keep to thank Dominic Delahaye for his collaboration on achieving this project. Uh, I'll start by mentioning the prerequisites needed to accomplish this project. First, we have the hardware components. In this case, I'll be using a single board computer, in this case, an Arduino Uno, to which I will attach different sensors. In this case, I'll have a sensor for humidity and temperature, and a second sensor for fire detection. I'll use two kinds of actuators, in this case two LEDs, a couple of LEDs, in addition to a second actuator that will be a servo motor. Of course, we will need to interconnect all these electronic components thanks to the help of wired connectors. In terms of software, the version of 4D we'll be using is 4D V18. In addition to its integrated 4D web server, for the development and design of our iOS application, we'll be using the 4D for iOS technology, which itself requires an Xcode version that's greater than 11.3.1. To program our single board computer Arduino, we'll be using the Arduino integrated development environment to accomplish this task. Optionally, we'll be using a Git technology. In this case, we've opted for GitHub for version control and distributed development. I'll present quickly the architecture of this proposed solution. So as we'll see later, this solution will have a 4D as its core element. It's the centralizing element in this architecture. From one side, we'll have a 4D communicating through a serial port channel with our single board computer, with our Arduino Uno. In another hand, we'll have 4D communicating with our iOS application, our mobile application, through a HTTP server or a web server. We must notice in this diagram that the arrows are both directions to represent that 4D, in fact, will work as an interface agent between from this left side, an interface agent between the mobile application and the single board computer, and vice versa. This interface will allow us to expose the data collected from the Arduino Uno and expose it to our iOS mobile application. I'll jump straight forward to a quick demonstration on the overall functioning of the proposed system. So I'll just jump to my other screen. So now, as we can see on screen, we'll have first our servo motor. We'll have two LEDs, each one representing a light bulb in our smart house rooms. We'll have the fire detection sensor as well as the humidity and temperature sensor on blue. We'll have, as we can see, the Arduino Uno single board computer that's connected via USB cable to our computer to allow serial port communication. Now, on the right hand of the screen, we can see that I am on a Mac OS machine, and I have already launched a simulator for an iPhone 11 Pro Max. This application will have an entry for each of the rooms of our smart house. So now I simply would like to turn the kitchen's light on, and I'll simply do that by just turning on this slider. So as we can see, the light has successfully turned on, and I'll just turn it off. I'll do the same with the living room light. I'll turn it on and turn it back off to save energy, and we'll see that these functions correctly as expected. For our garage, we'll have a motor that's represented by the servo motor, and that will just rotate accordingly, either we wish to open or to close our garage. For the humidity and temperature, we can see that we're already displaying it for each of the entries. We'll also choose to display it at the level of each of the rooms. So if we're on the kitchen, we can now see that the temperature is 25 degrees Celsius as of 7:16 minutes p.m. We have chosen an implementation choice was to only display the temperature and humidity if the values are changing. So if the values don't change, if we remain in a stable temperature or humidity, we'll keep displaying this same humidity and temperature. Now I would like just to refresh and see our current uh, temperature and humidity. We'll see it's the same. So I will simulate an increase in humidity. To see that the humidity is actually receptive. So now I've tried to increase myself the humidity, and as we can see, it has already got a higher value in this case of 72% relative humidity in our garage as of the current time. So this was a little demonstration of the functioning of this solution. Of course, we're successfully connected to our web server. In this case, the IP address of the web server has been mapped to this DNS. So our server is online because it has been deployed at the level of our 4D application. So now we've seen the functioning of our application, the overall functioning of the application. We'll just go back to our presentation and discuss all this functioning on more details. So now we've seen the demonstration, we'll proceed to describe and talk about the technical details of each of the components of this project. We'll start by looking at all the hardware needed in this project. So we'll have, as described, our single board computer, Arduino Uno, that will serve as a middleman between our computer and the electronic circuit. This will allow us to both receive data and send data to our electronic circuit. We'll see that Arduino Uno, for those who are not familiar with it, has a number of pins. In this case, we'll be using both digital and analog pins. The digital will be for the humidity and temperature sensor, while the analog pins will be used for our fire detector sensor. Of course, we'll be using as seen here in black and red, we'll be using, of course, a power to power our sensors, to power our LED bulbs, and also the ground for each of the electronic components. So we'll have the temperature and humidity sensor, DHT11, as we can see it's in here. So this little table describes the measurement range. We'll see that it can measure between 20 and 90% of relative humidity, and 0 to 50 degrees Celsius for the case of the temperature. The accuracy of the humidity is plus minus 5%, and the temperature, the accuracy is plus minus 2 degrees Celsius. The flame sensor is, in fact, an infrared spectrum sensor able to detect wavelengths from 760 nanometers to 1100 nanometers, always in the infrared spectrum. So this range is, in fact, the range where a flame is the waves emitted by a fire is located. So the first actuator will be a servo motor, the SG19. It's a rotary actuator that will allow to precise and control the angular position. This is the schema for those interested in probably recreating this circuit. So as we've seen, this is the flame sensor, the humidity sensor, both LEDs, and the servo motor. The Arduino Uno is connected with via USB. This is a more detailed schematic of the electronic circuit. So we'll have in more details that, for example, the humidity and temperature is well connected to the digital pin 1. Same with the LEDs that are both connected to the digital pins, represented here by D. On another hand, we'll see that the flame sensor is analog, and so it's connected to the first analog pin of our Arduino Uno, and we'll have a common voltage and common ground here, represented in green and red respectively. So what were the first steps on this project? So the first steps were to start or open a communication with our serial port channel. This was achieved easily thanks to the 4D command set channel to which we need to specify the port number and any configuration or any specifications on this port channel. After that, after the channel has been successfully established, we started to write the data to the serial port buffer using an Arduino sketch, of course developed or programmed with the Arduino IDE. And then we simply receive this buffer thanks to the command receive buffer. Here I have an extract of the Arduino sketch in which I simply write to the serial port, I print the value of humidity. So simply that, I'll add some delays and I'll write both humidity and temperature to our serial port buffer. This will after be received at the level of 4D thanks to the command receive buffer. So what's next? Once we have received the values, we have received the data buffer, we need to apply what we call with if-then rules, apply them to the received data. So we can have here a lot of applications. I've decided to call this project IoT and not Smart House because this project is in fact can be extensiated to other applications. So we can adapt this same logic to other applications such as farming, for smart agriculture, for example, to medical fields. So it's always the case that we just receive the data and we just condition over it. So in this case, I have a little code in 40 that will see that if the value is between 10 and 20, will send a fire mail. For example, in the case of humidity and temperature, will simply decide to save these values into our database. So once we have applied these conditions, we trigger our actuator. In this case, as we have seen, it could be sending a mail, saving the data to the database. We could power a LED or a servo motor. We could turn on or off a water tap, etc. It's really up to our imagination. It's really up to our application. This becomes really extensible. This becomes really general to any other fields. So, of course, the triggering action of an actuator can also be a user action. So, how do we actually trigger an actuator? How do we actually turn on a LED? How do we actually turn on a servo motor? So the first thing is necessary is to understand the bit ordering or endiness of the communication of variables between 4D and Arduino. So in this concrete scenario, in this case study, we had to convert 40 integers to blobs with long int, the command long int to blob, and the constant native byte ordering. Sending these blobs to Arduino was done with the command send packet, and it's then at the level of the Arduino sketch will need to receive this packet in a correct way. So in Arduino, just for note, bytes are big Indian ordered. So we need to have this in mind for receiving correctly the packets. So as we can see here, we'll intercept these sent blobs with an Arduino sketch, and we'll use this condition over this to trigger on an actuator. We'll start by this simple circuit composed of only one LED. So we'll read the incoming byte that's been written by 4D into the serial port channel. So we'll skip, as we can see here, the second byte. We'll just skip it just to have into consideration the Indianness of this incoming byte, of this blob, of this 4D blob. Once we've obtained the received integer, we'll just condition and treat it as hexadecimal, as we can see. Either it's 0, 1, or 2. In this case, if it's 0, we'll just turn off the LED. If it's 1, the received blob will turn on the light, the LED. And this is how we can send triggers to the actuators. So it's a collaboration between the code previously seen at the level of 4D and the Arduino sketch. So now what? Now we've been able to communicate back and forth with 4D and the Arduino board. Now we'll take this a step further. Now we'll start to design our database structure to store the state of the actuators and the data of the sensors. So we've seen that the state of the actuator, of the power, in this case the LEDs, we'll treat them as booleans, so we can after that at the level of our iOS application have directly this slider, and also to store the state of the bulb to know at each time either the bulb is actually on or off. We'll have also, with the same logic, a Boolean field for the motor. And finally, we'll have two fields, alphanumeric, to store both the temperature and the humidity values. Finally, a global stamp. This is added automatically by 4D for iOS configuration. So now we've designed our database. It's time to design our 4D for iOS application. So 44 iOS in this case will allow data visualization, manipulation, and synchronization between the actual application and our database. As we've seen in the demonstration, this 44 iOS application is connected to a 4D web server, and this is where the actual communication happens. This in this case, and as we've seen, the user interface was customized with Swift through Xcode. So in this case, we'll start to create our iOS application thanks to the iOS project editor. We'll publish the database table fields we've just created, and we'll simply display the sensor temperature and humidity values of these fields, as we've done here in this case. So we'll be adding also edit actions for each of the actuators fields. That's in this case booleans. So it's simply by adding these edit actions. That's 44 iOS. In the case it's a boolean, we'll know that it needs to add a simple slider. So as we've seen in the demonstration, to turn on or off a bulb, we simply needed to slide this slider on or off. So the most of most of the functional part of this iOS application was fully done thanks to the 44 iOS project editor. So now we'll see the core element, the core functioning element of this application. We'll see that it's the actual 4D. That will first allow us to deploy our 4D web server to expose the database to 4D for iOS, and also to receive requests coming from 4D for iOS. So once we've turned on the slider, we'll intercept this request, this 44 iOS request, thanks to the database method on mobile app action that will send us a object containing the request. So we'll simply parse this object request, and we'll use it to send or to trigger our actuators at the level of our Arduino board. So one problem that's very common when using single board computers is when communicating with single board computers using serial port channels, is that the access is in fact mutually exclusive. This means that we can have only one access at a time. So either we are writing to the single board, or we are reading from it. So we'll really need to handle this concurrency of read-write operation from to serial port channel. So this has been achieved thanks to hiring the abstraction of this serial port channel with objects. These objects, as we'll see, will be executing a worker. So at the level of these objects, we'll be defining the parameters, also the member functions that will allow us to hire the abstraction. Shared objects will also be used to allow access of this abstracted channel throughout all database processes. We'll see that this abstraction in fact comes in, as we'll describe later, in an object-oriented paradigm where we hire the abstraction of a very low level, in this case the worker, and the channel communication will be simply represented by a very elegant object with member functions with easily defined parameters. So we'll see that in this slide that we'll have these levels of abstractions. The worker will represent the lowest level. We'll have an object channel that will start to abstract these worker, so and the channel at the same time. So we can just write object channel just on or off. We'll do the same with Arduino to start a communication or to start the Arduino board. So we'll see these in more details in the next slides. So this is the how the abstraction works. So we've created a class called new Arduino, to which we pass as input parameters the port number and the configuration of the port. So this is what we'll have on startup method, and we'll just define our error callback, and our listen callback, and we'll simply, thanks to this higher abstraction, we just write Arduino start. We'll see how this is done. So what's actually inside new Arduino? So new Arduino has in fact object attributes definition. Will define the object attributes of the Arduino object. In this case, we'll see that the Arduino object will have itself another object called channel that will be represented by the attribute channel, and we'll have also, for example, inside this channel the byte order. For the channel class, we'll also be defining the object attributes. In this case, we'll have a number of parameters. This is the lowest abstracted object. So this one will have the most low level definition attributes. So we'll have if the port was successfully turned on, if the port number, the parameters, the byte ordering, the worker name, etc. We'll have defined already our shared object that will allow this mentioned access of the channel object throughout all database processes. And now, once we've defined both object attributes for the Arduino and channel class, we'll now define the member functions. In this same logic of object-oriented paradigm, we want this Arduino class to have member functions that will be easily, thanks to the dot notation, easily called. So we'll define the start, stop, on, off to turn on or off each of the actuators, the listen to receive data from our sensors, and we'll define a callback for our errors. So we'll see that in fact these are all methods defined at the level of our for the application that will simply pass as parameters of for the formula command. We'll do the same thing for the channel class. We'll define all its respective member functions. In this case, they'll be a bit different. We'll have a start channel and stop it. We'll have the option to send a value to the channel in the same logic to turn on or off our actuators, and we'll define our byte ordering in case we would like to change our machine or operating system, for example. So now all these channel member functions, same with Arduino, we'll see that they will have callbacks, which execution will be managed by the worker. So we'll have a series of callbacks, and that will be triggered on depending on the action. So if we're starting our channel, we'll invoke the onStart callback. The same with onData, what to do once we've received data, and what to do, what is the callback when we receive an error. So to do this, we'll mention the use of a worker. This worker will in fact be responsible of the execution of all these callbacks. So as we can see here, we'll start by constructing the worker. We'll define for each of the object attribute, we'll define which formula to execute, which callback to execute. And once we've actually constructed our worker, we'll actually just execute it. We'll execute it thanks to the command call worker. Of course, we'll make sure to know if the worker is already has already been executed or not. We'll set the channel, and we'll call the worker here, as we can see with the callback channel listen. What channel listen will do is receive the buffer sent at the level of our serial port, and at the same time the channel listen will do a kind of a recursive call, and will call itself again in the line we can see here, call worker channel listen. So this is the logic. So we'll recursively be calling channel listen callback until we receive a buffer. If we receive a buffer, so we'll do a different treatment. If not, we'll just call back our listen. Uh, of course, in case we want to send data to the channel, we'll make a similar procedure. We'll check if the worker is actually free, and if it's free, we just call the worker with a channel worker send. That will actually send a packet to our Arduino and use and make the concurrency of the shared object. So what's left now? We've used it to this project. We've been using a project mode. So this has allowed version control and distributed development, as we have all our methods as plain text. So this has allowed us to do this distributed development, where a team has been collaborating to get this project, to develop this project. Also, we have considered the execution of our 4D application on a headless mode. So actually, we don't see an icon of 4D executing. It will be running on the background. So this is makes our IoT solution with no human interaction. So for more details about headless application, please visit the blog article I have attached here. So what's our conclusions from these projects? What were our achievements? So this project is in fact a general project that can be easily instantiated to other fields or of study. So the same way we have decided with our humidity and temperature sensor to save its data, we can use this data with conditions to make an expert decision. For example, if we are on the field of smart agriculture, we would say that if the humidity value is below a certain threshold, we'll turn on the water tap. So this logic will remain the same all over the fields. So this project can indeed be easily instantiated to other fields of study. So we have decided to use this object-oriented paradigm. As we've seen, we've made use of object. We've built classes. We've attributed to these classes member functions as well as callbacks, and we've also, in the case of the workers, we've constructed this worker using the worker constructor. So we've also made this project easily extensible to other single board computers by simply changing the byte ordering, knowing the communication, how will the communication between our computer and the single board computer, and defining the correct byte ordering will suffice to plug in a new single board computer. Also, to apply this smart home scenario to a real high voltage circuit, we'll only need an electronic circuit a component, the relay, that will have help us do this transition from low to high voltage. I keep to thank you for your attention throughout this presentation. If you have any questions, please feel free to ask them at the level of the 40 forum. Our teams will be happy to answer your questions, and I really hope that this project could serve have served to feed your imagination for other projects on your applications. Thank for your attention.